Welcome to this explainer. If you really think about it, the human heart is basically the ultimate high-performance engine. I mean, it beats over 100,000 times a day, every single day. It never takes a break, and it certainly never shuts off for routine maintenance. And if the heart is that high-performance engine, then the mitral valve is arguably its most critical and definitely its most heavily stressed moving part. When this valve starts to fail, it's not just a medical issue, it is a highly complex mechanical failure. So today, we're going to look at the fascinating, incredibly high-stakes world of cardiac reconstructive surgery just to see exactly how master surgeons go about fixing this vital piece of human machinery.
Okay, let's dive right into this pre-op briefing. Our agenda today covers 1. Why repair? 2. Analyzing the valve. 3. The foundation. 4. Fixing prolapse. 5. Advanced techniques. And finally, 6, the final quality check.
Section 1. Why repair? First, we really need to understand the fundamental philosophy of modern cardiac surgery.
Now, you might be wondering, if a valve is failing, why not just rip it out and put a brand new artificial one in? Well, repairing the native mitral valve is actually the preferred standard of care over a full replacement, and there are some massive reasons for that. First off, a successful repair carries a significantly lower operative mortality rate. But even more importantly, repairing the valve completely avoids the lifelong risks associated with prosthetic heart valves, and it actually preserves left ventricular function. It does this by keeping the complex network of native cords, the subvalvular apparatus, completely intact. That means the natural geometry and the sheer strength of the heart chamber stay exactly the way nature intended.
Section 2. Analyzing the valve mechanics. Before a mechanic can fix a door, they obviously need to know exactly which hinge is broken, right? So before the surgeon ever makes a single cut, we enter the diagnostic phase. To map out this surgical battlefield, surgeons actually use a nerve hook to carefully examine the mitral valve apparatus. They're looking for areas where the leaflet is prolapsing, which basically means it's ballooning back into a space where it shouldn't be, or they're looking for where it's restricted. The valve is essentially divided into segments. You've got P1, P2, and P3 on the posterior side, and A1, A2, and A3 on the anterior side. One absolutely fascinating detail for surgeons to remember is that prolapse of the P1 segment is actually pretty uncommon. Because of that, the free margin of P1 is often used as this reliable baseline reference point to figure out just how severe the prolapse is in all the other segments.
Section 3. The foundation, remodeling ring annuloplasty.
Once the damage is mapped out, the real repair begins. Almost all patients dealing with chronic mitral regurgitation have this stretched out dilated valve opening, which is called the annulus. Because it's so stretched, establishing a rock-solid foundation is an absolute requirement if you want a repair that actually lasts. This foundational step is called a remodeling ring annuloplasty. The surgeon measures the distance between the commissures, which are basically the corners of the valve, and then selects an appropriately sized ring. Next, they place sutures circumferentially around the native annulus and right through the prosthetic ring. But let me tell you, this isn't just mindless stitching, it is a total minefield. The surgeon has to be incredibly careful, especially around the anterolateral commissure. One wrong move and they risk accidentally injuring the circumflex coronary artery or the adjacent aortic leaflets.
Naturally, the annulus is weakest along its mural segments, which is exactly why it dilates and stretches completely out of shape. That stretching literally pulls the leaflets apart so they can't seal properly. By cinching the tissue back down to this prosthetic ring, the surgeon perfectly restores the normal, physiologic size and shape of the opening. This drastically improves how well the leaflets meet, or co-opt, right in the center.
But there is real danger here. Sizing this ring is honestly an art form. If a surgeon selects a ring that is even a bit too small, they risk triggering the primary villain of our explainer, systolic anterior motion, or SAM for short. This is a terrifying complication where the anterior mitral leaflet gets sucked straight into the left ventricular outflow tract every single time the heart beats. It basically chokes off the main blood supply leaving the heart. Avoiding SAM literally dictates almost every single move the surgeon makes from here on out.
Section 4. Fixing leaflet prolapse. With our foundation secured, we move to the custom mechanical fixes for what's known as type 2 dysfunction. Specifically, we're talking about posterior leaflet prolapse, where a section of the valve has literally busted loose and is just flapping up into the upper chamber. The classic, time-tested approach to fix this is a mechanical cut and sew technique. First, the surgeon places temporary stay sutures around the healthy native cords to clearly map out the boundaries of the sick, flailing tissue. Then they identify the strict limits of the resection, physically cut out the bad segment, gather or plicate the annulus to shrink the gap, and finally sew the remaining healthy leaflets right back together.
Now, what's really interesting here is how they literally cut out this prominent quadrilateral chunk of prolapsing tissue. It's completely removed. Once that bad tissue is gone and the gap is closed up, the P1 and P3 segments are essentially brought back together to form a brand new, reconstructed, and fully competent posterior leaflet.
But you know, a large quadrangular resection isn't the only tool in the box. If the area of prolapse is less extensive, there's really no need to remove a massive square of tissue. Instead, surgeons can use a triangular resection. This excises just a small, highly precise triangle of the prolapsing edge, and then they simply reapproximate the free edges. This is great because it preserves way more of that vital native tissue.
However, as you can imagine, taking a scalpel to native leaflet tissue definitely has its limitations. The most obvious drawback, irreversibility. Once you cut it away, you simply cannot put it back. If a surgeon takes too much, they can accidentally create a rigid monoleaflet valve, narrow the opening, causing dynamic stenosis, or, you guessed it, once again trigger our villain, systolic anterior motion, because the remaining tissue has been pulled way too taut.
Section 5. Advanced Artificial Neochordae Techniques.
Because cutting away native tissue carries all those risks we just talked about, modern cardiac mechanics have developed some absolutely brilliant alternatives. Instead of cutting tissue away, they actually build new, artificial structural supports to hold the ballooning tissue perfectly in place. Let's see how this builds on that philosophy of preserving tissue. We have the posterior ventricular anchoring neochordal repair. Here, a super strong PTFE suture is anchored directly into the posterior ventricular wall, right beneath the leaflet. The ends are brought up through the prolapsed segment, pulling it down and folding it back on itself. This efficiently remodels and repositions the prolapsing leaflet without removing a single millimeter of native tissue. Incredible, right?
There are a few different ways to reinforce the valve. During a chordal transposition, a segment of the posterior leaflet and its healthy supporting cords are literally detached and moved over to support a failing anterior leaflet. Alternatively, when there just aren't enough normal cords to go around, artificial chordoplasty allows surgeons to fashion entirely new artificial cords. They use PTFE loops, tying them directly from the papillary muscles down in the ventricle right up to the unsupported edge of the leaflet.
Now, these artificial neochordae sound like the perfect solution, but they actually come with some incredible technical difficulties. The surgeon is working inside this tiny, incredibly challenging visual space. They have to adjust the distance of this artificial string to the precise millimeter needed to seal the valve. And the real kicker? PTFE is notoriously slippery. Trying to tie a knot exactly at the required length without it sliding and accidentally making the artificial cord too short, that requires a staggering level of judgment and pure skill.
If the prolapse is especially complex, there's another fascinating trick called Alfieri's technique, also known as the edge-to-edge repair. A simple figure-8 stitch is passed directly through the midpoints of the front and back leaflets, effectively pinning them together. This actually transforms the valve into a double orifice valve. So during diastole, the heart's filling phase, blood flows through two smaller holes instead of one big one. But during systole, the pumping phase, it completely prevents the leaflets from blowing backward.
Section 6. The final quality assessment.
Okay, so the structural repairs are done, the artificial cords are tied, and the ring is seated. But the operation is not over. Just like a master mechanic wouldn't let a rebuilt engine leave the shop without a serious pressure test, the surgeon must absolutely prove the seal is perfect. This happens right before the annuloplasty ring sutures are permanently tied off, which leaves the surgeon free to make any crucial last-minute adjustments. They pressurize the left ventricle with saline to force the newly repaired valve closed. They visually evaluate the symmetry of the closure. Sometimes they'll even trace the closure line with a surgical marking pen, then aspirate the saline to survey the exact margins where the ink transferred.
What they are really looking for during the saline test is a very specific measurement, 4 to 10 millimeters. This is the ideal depth of cooptation, meaning exactly how much of the two leaflets press flat against each other to form a watertight seal. If it's less than 4 millimeters, the seal is just too weak, and the surgeon has to immediately go back in to cut restrictive cords or downsize that ring.
But if that cooptation depth is greater than 10 millimeters, guess who returns? A depth over 10 millimeters is a massive red flag warning the surgeon of impending systolic anterior motion. It means there's way too much excess tissue, and the surgeon has to immediately intervene to reduce the height of the posterior leaflet to save the repair.
We've seen the annuloplasty rings, the quadrangular cuts, the incredibly slippery artificial neochorda, and those intense final saline pressure tests.
The probability of successfully pulling off these complex mechanical feats without triggering complications like SAM is heavily dependent on the surgeon's specific procedure volume. So as we continue to push the boundaries of preserving human tissue rather than just replacing it, it leaves us with a pretty compelling final thought. Medical engineering has given us the brilliant techniques to repair this vital engine part. But as the mechanical complexity of these procedures continues to grow, can specialized surgical training actually keep up to ensure every single patient has access to a true master mechanic?